Let's now do a two sample averages problem, and here's an example. 20 accounting majors recently took a stats exam. Their average was 85.9% with a standard deviation of 9.3%. In the same exam, 15 finance majors achieved an average of 79.1% with a standard deviation of 7.9%. Using a 5% level of significance, on average, are the accounting majors better at statistics than the finance majors? So we have our two groups, accountants and finance majors, and we have their means and standard deviations for that particular exam. Okay, so let's do that problem. First thing we're going to do is to write down the sample data. So we'll have accountants being the first group. The order that these get put down is not important, but once you've decided on who's one and who's two, just don't consider changing them. So there are 20 accounting majors. Their average score on the exam, which we'll call X bar 1, is 85.9%, and the standard deviation S1 of 9.3%. Finance majors we'll call group 2. There were 15 of them, so N2 is 15. X bar 2, right, their average was 79.1%, and the standard deviation was 7.9%. So S2 is 7.9. The question is whether the accounting majors are better. Alright, and that's a directional problem, so this is a one-tail test. And so the next step is to figure out which tail. Okay, so the way to do that is to compare the two sample averages. X bar 1, in this case 85.9, is clearly greater than the X bar 2 of 79.1. The greater than sign tells us two things. First, it's pointing up. Alright, so it's an upper tail test. It's pointing to the right, so there's an upper tail test. Also, that same symbol, the greater than sign, will appear in the alternate. So the alternate becomes a population equivalent of this. So instead of the sample X bar 1 being greater than X bar 2, we do the population equivalent, which is mu1 being greater than mu2. Also note that whatever happens in the sample for one-tail test, we put in the alternate. Okay, so in the sample, the accounting majors have a larger average score than the finance majors, so that's also true for the alternate here. So in the alternate, we can say that the accounting majors are better. You can either do that here or work it out below when we write down both our hypotheses. Alright, so writing down both. Alternate mu1 greater than mu2, and the null mu1 less than or equal to mu2. As we have above, the alternate, the accounting, is better, and for the null, the accounting is not better. Okay, it's an averages problem, so the next thing we do is do the degrees of freedom check. So N1 plus N2 minus 2. So N1 is 20 plus N2 of 15 minus 2 is 33, which is clearly greater than 30. So we're going to use z, or approximated with a z, and the large sample test. Alright, so the next step is to draw out distribution and find our critical value. So, Z distribution, center is always 0. It's an upper tail test with an alpha of 5%, so the 5% goes in that upper tail. So now let's go to the Z table, T tables, and find the critical Z value. One tail 5%. Alright, Z is the last row here. 5% is 1.645. Or have an upper tail test, so this is a positive 1.645. Alright, a quick version of the decision rule. If the z-calc is less than or equal to the positive 1.645, it's possible the accounting majors are not better. If the z-calc is greater than the positive 1.645, it's likely the accounting majors are better. Okay, so decision rule. Alright, so we're doing z-values. If z-calc is less than or equal to the positive 1.645, then the null is possible, so do not reject the null. It is possible the accounting majors are not better. Alternatively, if z-calc is greater than 1.645, alright, now we're sufficiently far enough away, we can reject the null. Alright, so the null is unlikely, and in its place accept the alternate. And for the interpretation, it is likely the accounting majors are better on average. Alright, now we're ready to do our calculations. For a two-sample averages problem, and this is a large, so this, as said before, this is an approximation, so s of x bar 1 minus x bar 2 is the square root of s1 squared on n1 plus s2 squared on n2, and so that'll be s1 9.3 squared divided by 20 plus 7.9 squared divided by 15, and squared. Now let's go to Excel to do the calculations for this. So this is equals the square root of 9.3 squared, put parentheses around that, divided by 20, plus parentheses for the 7.9 squared in parentheses divided by 15. And the answer to that is 2.913. So 2.913, and then we're ready to go to the Z-calc, which is x bar 1 minus x bar 2 sample difference minus mu 1 minus mu 2, the hypothesized difference, which is always 0, divided by the standard deviation s sub x bar 1 minus x bar 2. Alright, the sample difference is 85.9 minus 79.1. Alright, the hypothesized difference always 0, divided by the standard deviation 2.913, and let's go back to Excel to work that out. So this is equal to the 85.9 minus 79.1 divided by standard deviation divided by the standard deviation, and that's 2.334. So look back at our diagram. 2.334 is up here somewhere in the rejection region. So for our decision, we will reject the null. Since Z-calc in this case is 2.334, which is greater than the critical value of 1.645, we're now in the region where the null is unlikely, so we will reject the null. And accept the alternate. And say that it is likely that the accounting majors are better. At statistics. And that's the end of that test.